Good morning. My name is Payne Donaldson, and together with my thesis partner, Zachary Doerr, we will be presenting our thesis entitled Design of a Passive Shape-Adaptive 470 Class Centerboard. First, I'd like to thank our advisor, Professor Royce, for his guidance through this project, as well as our reader, Professor Golubeva, and our editor, Professor Lutz. We'd also like to thank Evgeny Bermatnov for supplying us with sample centerboards. I'll begin the presentation with the background and theory, after which Zach will discuss the procedure, results, make conclusions, and make recommendations for future work. The objective of our thesis is to design a 470 class centerboard, which exhibits greater bending torsion coupling than previous built centerboards. The 470 is an International 1 design with a set of class rules to keep all boats nearly the same. It has been featured in the Olympics since 1976 and will be included as a mixed male and female class in Paris 2024 and Los Angeles 2028. The 470 is a double-handed boat, meaning it is sailed by two people. It has a single trapeze, highlighted in red, which is characteristic of high-performance dinghies. It is known for extremely close and technical racing, and over the years, it has been the subject of many academic studies. This 470 has graciously jumped out of the water so we can see its centerboard. This appendage is the focus of our thesis. To understand its purpose and the effect it has on the boat, we have to discuss the physics of sailing. Sailboats are not capable of sailing directly upwind, so they must sail at angles. Wind over the sails produces lift, like an airplane wing, represented by F sail. Similarly, flow of water over the centerboard produces lift, FCB. The transverse components of these forces cancel, and a net thrust is produced. This accelerates the boat until it is balanced by the hull resistance and it reaches a steady state velocity. This speed of the boat is called velocity over ground. True wind angle is the heading of the boat relative to the wind direction, and leeway angle is the angle of the velocity over ground relative to the heading. Since the centerboard is a symmetrical foil, the leeway angle is required for it to produce lift. Velocity made good is the windward component of VMG. The goal of upwind sailing is to maximize VMG. VMG increases when velocity over ground is increased, a decrease in true wind angle, or a decrease in leeway angle. It's the job of the sailor to operate the boat in a way that optimizes VMG, but we can also increase VMG by optimizing the design of the boat itself. Our thesis focuses on improving the performance by reducing leeway. Leeway can be reduced in sailing dinghies by using a jibing centerboard. With a jibing centerboard, the entire centerboard rotates relative to the center line of the boat. This view shown is looking from below so that you can see the effect. In the 470 class, use of jibing centerboards is specifically prohibited, so we must use a twisting centerboard. For a twisting centerboard, the root of the board is fixed to the center line, but the hydrodynamic pressures twist the tip, achieving a similar effect to a jibing centerboard. With a conventional centerboard, the angle of attack, or AOA, is equal to the leeway angle. When the centerboard twists, the average angle of attack remains roughly constant, but the twist angle T reduces the leeway angle. Since the flow is more in line with the hull, the resistance is reduced and the magnitude of the velocity through the water will increase. Ekstrom and his associates at Chalmers University of Technology found that twist improves the performance up to an optimal angle of 8 degrees. The 470 class rules specify the parameters a centerboard must meet in order to compete, but they do allow for variations in the shape and weight within the specification. The class rules also limit the materials to wood, foam, fiberglass, polyester resin, and epoxy resin. There's no limit on how these materials are used, which allows us to optimize its construction. The allowed materials give us a variety of mechanical properties. Some materials can be classified as isotropic, which means their stiffness and strength are the same in all directions. The isotropic materials we can use are all polymers. This includes the epoxy or polyester resin and foam. Orthotropic materials have different stiffnesses and strengths in mutually perpendicular directions. The materials we can use with orthotropic properties are wood and fiberglass. A composite material refers to any combination of materials in a single structure. Fiber reinforced plastic, or FRP, uses glass fiber as reinforcement set in an isotropic matrix, in our case, polyester resin. Together, the reinforced composite exhibits orthotropic behavior, and the combined material properties are far superior than either component alone. Fiberglass is available in a variety of different forms. The fibers can be woven into a textile cloth, or they can be arranged into unidirectional plies, which only have strength in that 0-degree axis. They can also be arranged in a biaxial pattern with plies at 0 and 90 degrees to give strength in 2 directions. Unidirectional and biaxials are referred to as stitched reinforcements. Stitched reinforcements have superior properties to woven reinforcements because they avoid the weaving and crimping of the fibers that is present in the weave. For this reason, we try to use stitched reinforcements as much as possible. So how do we get an FRP centerboard to actually twist? The centerboard is a sandwich structure with a lightweight foam core between 2 fiberglass skins. We can design the properties of these fiberglass skins to make the centerboard rotate in torsion as a bending load is applied. There are 2 ways we can do this. The first is by using off-axis laminate plies represented by the angle lines on the top surface of the plate shown. And the second is by shifting the shear center by reinforcing one side with stiffer materials represented by the red-colored core. We define the ply angles according to the example above. The plies are referenced relative to the leading and trailing edges of the centerboard. This example represents a biaxial reinforcement angled at 30 degrees. The red lines represent a positive 30-degree angle, while the blue lines represent the perpendicular ply at negative 60 degrees. Using equally angled plies on both sides of the beam produces the bending torsion coupling. Since the fibers are not aligned with the length of the beam, the bending strength is significantly reduced. Our design must achieve maximal twist while retaining bending strength. Higher twist angles will require thicker laminates. Extrum used off-axis plies to produce 0.8 degrees of twist in a 470 centerboard using plies rotated at 28 degrees. Professor Julie Young at the University of Michigan modeled and tested carbon fiber high aspect foils with a 30-degree ply angle. In the flow channel, they achieved up to 5.1 degrees of twist with their model. The other method of twisting the centerboard is by shifting the shear center. This can be achieved by adding fibers near the trailing edge and by increasing the core density and stiffness near the trailing edge. This shifts the shear center aft, increasing the distance between the shear center and the center of pressure represented by F hydro, which creates a torsional moment to bend the board. In order to design the structure of our foil, we turn to potential flow to solve the hydrodynamic forces. Potential flow is inviscid, irrotational, and incompressible. It treats the flow as a superposition of free stream flow, sources and sinks, and bounded vortices. The analysis requires the Kutta condition to force a stagnation point on the trailing edge of the foil, which allows the calculation of lift based off of the circulation of the vortices. Since the potential flow is inviscid and irrotational, there are no boundary layer effects. To bring this 2D theory into 3 dimensions, we utilize the vortex lattice method. The vortex lattice method entails discretizing the wing into panels, each of which contain a bounded vortex. A tangential flow condition is applied to the panels, preventing flow through the wing's surface. The flow is then resolved, satisfying Laplace's equation, and the circulation on each panel is then known. So the lift can be calculated and creating a pressure distribution. Although potential flow is inviscid, in a software like XFLR5, viscous corrections can be implemented to capture the effects of the boundary layer on the low pressure side of the foil. With a method to determine our loads, we can now discuss the structural side of the problem. A finite element analysis model was developed in SOLIDWORKS, and SOLIDWORKS allows us to set up the problem, which entails discretizing the geometry into mesh, designating composite layup properties on these mesh elements, defining loads, and defining boundary constraints on the problem. SOLIDWORKS can then solve the problem using the finite element method and post-process the results so we can visualize and evaluate the stresses and displacements. I will now invite Zach to continue with our procedure.
Thank you, Payne. Our procedure began with a survey of existing centerboards provided by Evgeny. This is to determine their geometric and mechanical properties. After this, we set up a model in SOLIDWORKS FEA, and then we validated this model using data from the centerboard survey. We then began our design iteration. We looked at two load conditions, one when trying to right a capsized 470, and the other when sailing upwind. Our survey of the existing centerboards began by 3D scanning to determine the geometry. We used Einscan 3D scanning software. The scans were exported to Rhino for better modeling, and these scans would be used in the potential flow analysis and the FEA. Additionally, we conducted a bending test on the centerboards at hand. For this, different centerboards were clamped to a table, and various weights were applied to the end. We used a ruler to measure the deflections at both the trailing and leading edges of the centerboards, and any twist which was exhibited could be calculated using the difference between the trailing and leading edge displacements. Finally, we did our best to determine the laminate schedule of the existing centerboards. This involved sanding through all the layers of the laminate of the existing centerboards and using calipers to measure the total thickness. The thickness of each layer of the laminate was estimated based on the total thickness. Additionally, we measured the angle of each ply. The finite element model in SOLIDWORKS utilized a solid element for the core and shell elements for the laminate. The shell elements could be defined as composites in SOLIDWORKS, which allowed us to adjust the number of plies that they represented, as well as the thickness, material properties, and rotation angle of each ply. These elements were bonded together, and then we could apply our constraints and our loads. The constraint for this was a fixed condition at the root, where translation and rotation were disallowed. In this example, the load shown is in the right-hand case, with a load applied at the tip. After this, a mesh was created. When creating the mesh, it was important to perform a convergence study to determine an adequately small mesh size. An adequately small mesh size means that the results are accurate, but too small of a mesh size would unnecessarily increase computing time. Down the left column, you can see the mesh size decreasing from 50 millimeters to 10 millimeters in increments of 10. The middle four columns show the leading and trailing edge deflections as predicted by the FEA, as well as a percent change from the previous mesh size. And the right two columns show the maximum von Mises stress, as well as a percent change from the previous mesh size. Between a 20 millimeter and a 10 millimeter mesh size, the percent change in the leading and trailing edge deflections were both under 1%, while the percent change in the maximum stress was only 3.2%. This meant that a 20 millimeter mesh size was sufficiently small to perform an accurate analysis. For reference, when moving between a 50 and a 40 millimeter mesh size, the change in the maximum stress was 22.5%. After setting up the finite element model, we could validate it using the data from the existing centerboards. We recreated the geometry and the layup of the existing centerboards in our FEA model and applied the same load in the FEA as in the bending test. The deflections from the FEA and the bending test were compared. In the SOLIDWORKS model, the leading edge and trailing edge displacements were both just under 3 inches, while in the bending test, they were both just over 3.5 inches. At the leading edge, this represents a difference of about 20%, with the FEA underpredicting the bending test results. At the trailing edge, the deflection is also underpredicted, but only by a factor of 17.5%. Potential inaccuracies in our FEA validation could result from inaccuracies in our deflection testing. We noticed at one point in the deflection testing that the table was having a tendency to lift some of its legs off the ground. We believe that this increased to the deflections measured there. Additionally, in our FEA model, we did not make a correction for the gel coat thickness. In our current model, the gel coat thickness is included in the total thickness of the laminate, despite the fact the gel coat contributes minimally to the mechanical properties of the centerboard. Finally, it is entirely possible we made an error in recreating the layup, as it is difficult to know the exact thickness of each ply, and the material properties are incredibly difficult to predict without knowing the resin content of the centerboard. After validating the model, we began our design iteration. We looked at two load cases, one when sailing the boat upwind and the other when riding a capsized boat. In the sailing load condition, the force produced is from hydrodynamic lift as the boat moves through the water. Since this is where the performance matters, this is the condition that we optimize the twist angle at. The other condition, the riding load condition, is where we would expect the centerboard to fail. In this condition, a point load of 1 kilonewton is applied at the tip of the centerboard, roughly 945 millimeters from the root. For reference, 1 kilonewton is about the weight of a heavier set soaking wet 470 sailor. In the riding condition, we checked the factor of safety on the ply stress as well as the core shear stress. We aimed for a safety factor of about 2. For the sailing load condition, we obtained the pressure distribution using XFLR5, a potential flow code. This process begins by analyzing different cross sections along the span of the centerboard in a two-dimensional analysis across a range of angles of attack and Reynolds numbers. The results from this are then interpolated and three-dimensional effects are added in a second three-dimensional analysis. For the 3D analysis, it is important that the centerboard is mirrored about the x-axis to mimic the end plate effect of the hull. Similar to the FEA, a convergence study was performed to ensure that we had a correct number of span-wise and chord-wise panels to accurately represent the pressure distribution without adding unnecessary computing time. After obtaining the XFLR5 output, we had to export to MATLAB and find a 3D regression of the pressure distribution. This is because the export from SOLIDWORKS or from XFLR5 is in the form of a comma-separated value or CSV file, while SOLIDWORKS FEA only accepts distributed pressure loads in the form of an equation. For the initial analysis, we assumed a 5-degree leeway angle and 5.7 knots of boat speed. This is the same assumption that Ekstrom and his associates had used in their previous research on twisting 470 centerboards, and they obtained this data by analyzing the performance of 470s at a World Championship regatta. After obtaining the pressure distribution, we ran the FEA, and we analyzed the deflections in the twist. We then had to recreate an XFLR5 model with the deflected, twisted centerboard as it changes the pressure distribution. It is important to note when rerunning the XFLR5, the angle of attack has to be altered to maintain the same overall lift force of the centerboard. This also allows us to analyze the actual reduction in leeway that our centerboard would produce. We repeat this process until the pressure distribution and the twist converge on single values. Our design process began by optimizing the laminate thickness at different ply rotation angles. As a ply rotation angle increases, since the fibers are less aligned with the principal stresses, it is necessary to add more laminate thickness in order to maintain an adequate factor of safety in the riding load condition. We began by looking at the riding load condition and finding the minimum ply thickness, which would give an adequate factor of safety. We then tested these ply rotation angles and laminate thickness with the sailing load applied to see which would produce the maximum twist. In the future, we will look at further optimizing the layup by adding additional plies and higher density foam near the trailing edge. We will do this only with the rotation angle that produced the best results in phase 1. This is an example laminate schedule of a centerboard. On top is a gel coat. This is not modeled in the FEA as it does not contribute significantly to the performance of the centerboard. Underneath is a single 8-ounce cloth. Having a layer of cloth helps produce a better gel coat finish. Underneath is a series of unidirectional fibers at the specified rotation angle. We add extra unidirectional fibers if the safety factor is not sufficient. We tried to incorporate a few biaxial fibers as well to help prevent cracking in real-life application. However, we have observed that biaxial fibers significantly reduce the twist of the centerboard, so we tried to keep its use at a minimum. Finally, there's the foam core. Our initial results showed that a maximum twist angle was achieved in the righting load condition at 0 degrees of ply rotation angle, and that in rotating the plies in either direction resulted in decreased twist. Here are the same results, but for the sailing load condition rather than the righting load condition. In the left column, you see the ply rotation angles. The middle column shows the leading and trailing edge deflections, and the final column shows a calculated twist. Again, a 0 degree ply rotation angle in our initial study resulted in the most twist. These results do not align at all with the theory. In theory, a positive ply rotation should produce increasing amounts of twist up to a maximum between 20 and 35 degrees of ply rotation. A negative ply rotation angle should produce negative twist up to 20 or 35 degrees of ply rotation. At 0 degrees of ply rotation, the twist should be 0 or minimal. Our results, on the other hand, had a maximum positive twist with no ply rotation angle, and positive twist using positive and negative ply rotation angles at decreasing magnitudes. To begin analyzing what went wrong with our initial study, we performed a simplified study. This utilized a centerboard that did not have foil-shaped cross-sections. For this analysis, we also kept a constant laminate at different ply rotation angles. We did not adjust the thickness to maintain a safety factor. This model behaved more as expected, showing minimum twist at a 0 degree ply rotation angle and a maximum twist at a 25 degree ply rotation angle. For reference, here are the two results side by side. As you can see, our initial results did not behave at all as in the simplified study. We performed further analysis to analyze what went wrong, and we determined that the discrepancy was likely caused by the way we had modeled the centerboard. Initially, the geometry had discontinuities along the span of the centerboard, which we assumed would have been handled properly by the FEA when bonding the mesh. It appears this is not the case. We redid the model with a geometry continuous along the span of the centerboard and got these results. This is for the righting load condition, and as you can see, at a 0 degree ply rotation angle, we have 0 twist, and we achieve a maximum twist in the righting load condition of just under 5 degrees with a 22 degree ply rotation angle. Here is the results of the simplified study side by side with our new results. The difference in the magnitude of twist is caused in part by the foil-shaped cross-section in the new results, and in part by the fact that the new results involve the use of thicker laminates at higher ply rotation angles. In conclusion, the initial results did not behave as expected. After performing additional analysis, we concluded that in order to capture bending torsion coupling effects in SOLIDWORKS FEA, the geometry must be continuous along the span of the centerboard. We are currently reworking our way through the design iteration process using the corrected model. We have not tested with the sailing load condition yet. As of now, a 22 degree ply rotation angle appears to be the most promising. In the future, we plan to continue by analyzing trailing edge stiffening. Recommendations for future work include further optimization of the layup using a fluid structure interaction tool, the development of a build and test procedure to validate our results, an investigation on the performance effect of twisting centerboards, whereas for our analysis, we simply assumed that more twist would result in a better upwind performance, an investigation of the dynamic response of the centerboard, and a simplified parametric study of bending torsion coupling effects. Thank you for listening. I would now like to invite Evan Spalding up to present his thesis. Please hold all questions until the end.